All right, well, good afternoon, everyone. I'm delighted to come and talk to you about all the great things that the Webb telescope will be doing for you and transit spectroscopy in the future. Transits, of course, aren't the only thing exoplanet related that will be done with Webb, but I'm going to try to provide here for you is a high-level overview of all the different ways you can probe transiting exoplanets with the James Webb Space Telescope. You've already had a lot of excellent talks about the transit method in general and the types of planets that we look at and the questions we're trying to answer. So this is just here, we've learned where we are now, and then this is how it's going to look in the future. But I want to start with, this is my clicker, yeah. Making everyone aware that the James Webb Space Telescope really is quite an engineering feat. I think Drake showed an image this morning of JWST, but this is to put it into scale. So there's a human being. There's the Hubble mirror. And then there's the JWST mirror. Mirrors. So this is a very large telescope that we're going to send into space. And it's going to have to do some drastic feats of unfolding after it has to be folded up to fit into the fairing. So I want to let you just see this little sort of 2.5-minute movie that shows you what happens after they launch Webb and it has to sort of unfurl and get out to L2. So we'll just start that up. So it's already been launched, and you can see the elapsed time up there on the top. And this is sort of in fast mode. There's another version of this, if you search online, that's like a 12-minute extended one. It has a very Morgan Freeman narration with it. But this one gives you the basics in a short amount of time. You can see how it's still on its way to L2, and it's starting to unfold itself here. So one little flap. And then the antenna deploys. And I want to highlight that antenna. Who here has worked with Spitzer? So when you need to downlink data, you have to roll the whole telescope back and forth. James Webb, of course, has an antenna here that's movable. So this allows you to not have to rotate the whole spacecraft to downlink data. It also allows you to actually downlink data while you're still observing. All right. So this is the sun shield and what we call the tower deployment. So these are all very scary moments for us after launch. There's a lot of moving parts here that has not been attempted before with missions like Spitzer and Hubble or even Kepler. And there goes the sun shield other side. Tighten up. The sunshades. So there's 5 layers in there. And then we lower the boom. And this is the best part coming up, where you open the wings of the mirrors. So again, that mirror is so big that you had to fold part of it back to get it into the fairing. And it continues on. So notice that's 30 days. Up there, the clock is ticking. All right, and now it's going to go into its orbit. So I just want folks to appreciate there's been a lot of really excellent engineering work to make this happen and to enable the great science that's going to happen with JWST. So as I pointed out, and I want to highlight this again and again and again, a lot of these advances that were made for JWST are going to be really excellent for transiting exoplanet science in general, even though that may not have been the original goal of that design. And one of those is, of course, the steerable high-gain antenna. And then, of course, its orbit in L2 will be excellent. So we've been doing really excellent work with HST, but we've always had to deal with the fact that you're on this 90-minute orbit, so you're chopping up your transits. We're going to have really high fidelity data coming down where you can have these very large continuous observations. And then I want to orient you just a little bit about how all of the JWST detectors operate. For those of you that have used Wide Field Camera 3 on HST in the past, this will be very familiar. All of the instruments operate using non-destructive reads that sample count rates up the ramp, as we call it, okay? So when you're planning your observations, there's going to be lots of terms floating around, and they get used interchangeably sometimes and cause confusion. But the thing to keep in mind is that for a single integration, so a single sort of point in time, you'll have a number of samples up the ramp, or groups in this case. Each of those groups for bright objects will typically consist of one frame. Okay, in other cases, for not bright targets, they may use more frames. So for time series observations, like with transits, you'll have a number of integrations, and that will constitute a single exposure. Okay, so I just threw a lot of terminology around, but these are the sorts of terms that you'll see as you're planning your proposals, and also in a lot of our exposure time calculators, etc. Okay. So Drake did put this plot up earlier, but this just gives you an idea of the complement of the Webb spectroscopic modes. There's a lot of them. There's actually a few that aren't even on the plot that I'm showing here. In addition, there's a lot of imaging modes, which I'm not going to talk about today, but I think it's worth your time at some point to go through and just look at all of the different ways that you might be able to use Webb, even if it's not in the ways that I'm highlighting today. So the complement of instruments on JWST cover the wavelength range from 0.6 all the way out to 28 microns. So you have 3 instruments that are operating sort of in the near infrared from about 0.6 to 5 microns, and that includes the NearSpec instrument, which I mentioned earlier this week, and so did some other people. NearSpec, okay, which covers this whole 0.6 to 5 micron range using a variety of high resolution settings, and NearCam, so 3 instruments in the near infrared, and then MIRI is the one that gives us the 5 to 28 microns. I'm going to focus on what's called the low resolution spectrograph, or the LRS, with MIRI, because this is the one that's actually been made to operate in a slitless mode, and will probably be the workhorse of transit studies at those wavelengths. All right. So let's start with NearSpec. This is an instrument, as I said earlier this week, that was purposefully designed to do transit spectroscopy. And here's a simulation of NearSpec being used to look at GJ1132b, and we're going to assume that it has a CO2-rich atmosphere, no clouds. But with SOS, what you end up getting is sort of at an R of 70, you can certainly make out these spectroscopic features. It only requires about 5 visits and about 21 hours of wall clock time. At this point, looking at 1132 with HST is going to require a far greater investment of time, but it's certainly worthwhile to do pre-screening. All right. So let's look a little more detail at the NearSpec instrument and why it's so magnificent for transit work. As I highlighted before, that's kind of faint up there. In the spatial direction, it has this very broad PSF that will make it less susceptible to effects of jitter, etc., and also saturation. So this is what the PSF looks like, the Batman cowl, and here's it spread out on the detector. The NearSpec traces are here, and for those of you who've done the hands-on session, you've become quite familiar with this. Here's your first order and your second order. So your first order goes from about 2.8 microns to about 0.85 microns. And here's your second order right here. And your second order is the one that's going to give you your 0.6 to 0.85 microns. There are 2 different subarrays you can use with it for NearSpec, and one is intended to be sort of the nominal mode, and that's the 256 by 2048 that's outlined in purple here, and that allows you to get both the first and second, capture both the first and second order. It has basically a saturation limit of about JMAG of 7.2. But keep in mind that that means that only a portion of the spectrum is saturated. So you can certainly go brighter than that, knowing that you'll still have information sort of shorter and longer wavelengths in this case. There's also the smaller subarray, which is a 96 by 2048 substrip, with a bright limit of J of 6.2. Okay. The NearSpec team has done a lot of great work making tools to help folks better understand what transit observations will look like. This is a screenshot from their 1D simulator, which I'm going to pull up here. And they also have a very nice trace contamination tool. Let me see if I can pull it up. Where did it go? Okay. Well, let's see if I can do this correctly. I need a space, right? After that, okay. So you'll have the slides. You can go do this at your leisure. But you can actually pick your favorite target, and it will import all of the relevant information about the star, etc. You can pick what sort of planet atmosphere you want to assume. And right now we're just going to do a generic hot Jupiter and scale the model. And let's go down. And then in this case, we'll run the simulator. And then it makes a lot of really great plots here. So it'll actually show you what your spectrum will look like. It's taking a little while to load. This is a PDF. It shows you where things are saturated. In this case, because I selected it to have in groups of 2 or 2 samples up the ramp, some of this spectrum is saturated, but you can go back and try different realizations. So you can see where all the different plots are. You can go back and try different bennings. So I suggest everyone try that. The other key tool here is what's called it's a planning tool. Most of these modes I'm going to talk about today, except for the ones on NearSpec, are slitless, which means you can get contamination from spectra from other nearby sources. And you really need to take that into consideration when you're planning your observations and what your basically your phase and roll constraints are for the telescope. So there's already a lot of great planning tools for you to start thinking about observations with instruments like NearSpec. And I'll get to another tool later in the talk. Let me get back on here. Okay. But certainly all of the instrument teams are very interested in engaging the transit community and helping them to plan the best observations that they can with their instruments. So we're going to move on to the NearCam Griz Ohms. Okay, so these again are slitless. The combination of the Griz Ohms actually allow you to cover 1 to 5 microns. And I'll explain how that has recently been achieved. This is a great recent SPIE article by Tom Green, who's right in the audience, that shows sort of a generic hot Jupiter. I think it's HD209, right? Generic hot Jupiter at NearCam. You require 2 transit observations because you get 1 to 4 microns all in one go, and then you have to go back and reobserve it to get 4 to 5 microns. But this is a really excellent observation. I mean, you can see the spectral features. You know what's there. And this is going to be amazing. So for the investment of 2 transits, you get this sort of high quality look at hot Jupiters and beyond. So how do the NearCam Griz Ohms do that? Well, there are 2 settings, and the one that's going to be available in cycle 1 are the long wavelength Griz Ohms. Okay, and here's a look at the trace. These are going to be very, very familiar to those of you who have used wide field camera 3 in the non-spatial scan mode. They look very, very similar. And then they need to be paired with any number of filters. The main ones will be this F322W2, which will give you basically 2.5 to 4 microns, and then the F444W, which will give you, did I get that backwards? Oh, no, 4 microns, yeah, 4 microns to 5 microns, sorry. There's also a number of different subarray options that allow you to control basically your frame time and then, of course, your integration time. You can go to very small sort of substrips for very bright targets from 64, 2048, all the way up to using the full frame for some fainter targets. Especially for bright targets, you can consider using this stripe mode output or 4 amp read, where basically in the detector you have these 4 columns that are read out by different amplifiers. So that decreases your frame times, so you can look at brighter objects Okay, so this is the nominal Grisms that will be available in cycle 1. You can easily pair these with the nearest source observations to get the full coverage from 0.6 to 5 microns. There's been a lot of work recently to use something that was really never intended to do science. These are called the dispersed Hartmann sensors, or DHSs, and they're actually Griz Ohms that are used for wavefront sensing on the top. So these are the different submirrors here, these little hexagons, and the way that they're aligned is using these Griz Ohms here. And this is what those 10 Griz Ohm spectra look like, and they cover the wavelength range from 1 micron all the way out to 2 microns. Well, these can be really, really useful for especially bright sources because you have your source then dispersed over 10 different spectra. So we're working to hopefully make it available in cycle 2. But stay tuned, because this could be one of the most efficient ways to cover the whole 1 to 5 micron regions. So the especially great thing here, so here's the DHS bright limits. So I'm hard pressed to find anything that can't be observed with the DHS. If someone can come up with something, let me know. So. And there's the bright limits here for the long wave with Griz Ohms and the 4 amp readout pattern are also very good. So Kmags of 4, 2, etc. And here's it plotted. So this is for the longest, the 444W, against the current transiting exoplanet population that has masses and radii, so ones we might want to characterize. And if you're using 2 samples up the ramp in the smallest subarray, you cover the entire current population of exoplanets. So bright limits are a non-issue here, and a non-issue in general. And you can go find more information here, which is where I pulled this plot from. All right, so that was NearISS and NearCam. Now let's move to NearSpec, our other near-infrared instrument. And this is the mode that will give you the highest spectral resolution. Okay, the other ones were sort of R of 700, R of 1,000. Here you're looking at something more like R of 3,000. So they have a combination that covers the whole 0.6 to 5 micron range. And these are just some simulated planetary spectra at the sort of native, well, bend down just a little bit, resolution. It easily allows you to tell the difference between a number of different atmospheric scenarios, inverted, non-inverted, different heat redistribution efficiencies. So these again are theoretical eclipse spectra, so thermal emission from the planet. So NearSpec has a fixed, we'll call it a slit. They actually designed this nice large aperture box right here for these sorts of studies. So again, I think it's important for people to keep in mind that transiting exoplanets were in the back of people's minds when a lot of this development was happening, and that, of course, was not the case for Spitzer and Hubble and other missions. So you have this nice, nearly slitless opportunity here. Forward. And here are the various Griz Ohms that are available. So you have several high resolution. You can see what the resolving power is here. Some medium, and then this is the Prism. And I want to mention the Prism just briefly. It has about an R of 100, but it does give you access to the full 1 to 5 micron all in one go. The one limitation is that for the Prism, so the Prism is the black line here, and this plot here again is the limiting J-band, so before you saturate versus stellar effective temperature, and you've got the whole population, and this is sort of a population of what tests might find. This assumes that you're going to use 2 samples up the ramp. You are allowed to use 1 sample. There are caveats and things you should worry about if you go into that regime. But with a Prism, you won't really be able to look at stuff much brighter than a JMAG of 10. But as you can see, that's still a significant portion of the population. But it is the probably most optimized way to go from the whole 1 to 5 micron range. All right. So MIRI, I'm going to highlight the LRS here. It does have a number of other spectroscopic modes that I encourage you to investigate. I don't think they've been labeled as what we call time series compatible. Is that correct? This is the only time series mode, right? Okay. So there may be work that needs to be done in the future. But what I have plotted here is a theoretical eclipse observation. And as Drake pointed out, there's going to be a lot of really great eclipse observations done with JWST. Again, for a simulated GJ1132, assuming pure CO2, and with about 10 Miri eclipses, you can actually measure this whole range of spectroscopic features here with high fidelity. I want everyone to keep in mind that this is the first time that we're going to probe exoplanets in transit beyond 5 microns since the end of the Spitzer cryogenic mission. And during the cryogenic mission, there were only probably 1 or 2 that we actually studied in detail. So this will be our first chance to really understand the behavior of exoplanet atmospheres at these longer wavelengths. Right. So just a little orientation of how this works with Miri. You have the detector. Over here is where they're going to have the slitless spectrum, which is nicely against these reference pixels, which should help with your systematic corrections. Again, I'm showing over here saturation limits. So this is K-band magnitude of the host star. Here's its log T effective, and here's the current population, assuming a number of different groups or samples up the ramp. So in groups of 1, 2, 4, 10, or 30. And for the LRS, you can certainly get up to about 5.5. This assumes that you don't want to saturate any part of your spectrum. If you're willing just to saturate just a tiny bit, say you only get 6 to 12 microns, you can go all the way to the top, basically. So it's important to consider what saturation means in the context of spectroscopy, because it's not always entirely straightforward. I also point out that the Miri team put out a series of papers, and you can start by looking at this one. It's a really great series of papers, and if you want to know more about the Miri instrument, I encourage you to read those. All right. So I've just introduced you to all of the various instruments, and you may be scratching your head and say, well, I only saw that SOS has this wonderful online tool. We're in the process of releasing the exposure time calculator. It's called Pandya. It has a fairly nice sort of web-based interface, but it's not particularly optimized for transits. And there's been a side project going on that's been done predominantly by Natasha Batalha at Penn State to make a interface for exoplanets for Pandya. And so we call it Pandexo. And I'm going to give you a little, this is a movie actually, I think it started here, of what Pandexo does. So we're going to start a new calculation. You're going to call it something. There we go. So you can actually put in your own stellar spectra, your own planetary spectra. So the nearest SOS template comes with a lot of really great preloaded stuff that makes your life easier. Magnitudes. This one doesn't pull from the exoplanet archive the way the nearest SOS does. So here it goes, putting the planet model in. And there's a range of different input parameters if you're choosing centimeters for some reason, or RP over R star. So you can choose the units of your input planet spectrum. You can estimate the number of transits you need. There's some really relevant information about the efficiency and saturation limits for the various instruments at various wavelengths, just to give you a ballpark of what's going to happen for your particular target. Then you'll select your instrument. That was just showing what the full well is for each of the instruments. Okay. You can put in a noise floor. I don't think she put one in. But we're in the process of getting some good estimates of what we think the noise floor should be for each of these modes, so you can input that as well. And then it will do this calculation. And is that done then? Okay. So it's running, and then you'll get something that looks like this. Okay. It's a lot. It's like drinking from a fire hose, trust me. It's a lot of information, but it does give you your spectrum over here, and perhaps more useful, you can use this output to go a little bit further into playing with your model in this context. So basically you've now loaded up your output from that previous phase. And you're going to look at a couple of things. Right now it's at the native resolution. So you can see the underlying planet model when you zoomed out, see the gray stuff on either side. And then you'll look at binning. And it will also basically output underneath your various binning scenarios, what the SNR is, the achievable precision, etc. Okay? So hopefully this tool will be released widely by the end of this year for everybody to start using. All right. And anything else? Okay. I also want to mention sort of the other parts of how transiting exoplanets will be handled with JWST, and that includes planning your observations, the pipeline, and the archive. Basically, we now have basically a time series observation designation at every phase of planning your observation for JWST to putting it into the astronomer proposal tool. When the data get delivered, they'll be flagged as time series observations, and that's how they'll travel down the pipeline, and that's how they'll be flagged and delivered to the archive. So for the first time, you're going to have your data processed in a way that's relevant for time series data. And one of the ways that we've done that is in the astronomer's proposal tool, there are templates for time series observations, and they automatically do not have dithers, and they don't complain about the exposure time. I use Spitzer Spot a lot. I get a very unhappy leopard a lot of times. I don't know if folks have done this. It just yells at me like, why aren't you dithering? Why are you staring for so long? You will not get those complaints if you're using the appropriate time series templates. These templates also allow you to have exposures that exceed the quote-unquote 10,000 second rule. And so every 10,000 seconds, they're going to need to move the antenna. So there will be slight disruptions in your data, and we're still trying to understand the magnitude of that effect. But you'll be able to go back and identify those occurrences of the moves of the antenna and correlate that with any noise in your data. All right, and I put a little link right here. You can actually download the astronomer proposal tool right now. And all of the time series templates are in place. So I encourage you to go and try to plan an observation. All right. So again, so you've just planned your observation using the ETC or whatever homegrown code you want, and you've put it into APT, and it has been selected, and now you're getting your data down. Your data will flow through a very specific part of the pipeline, and this is going to be a pipeline that goes beyond just basic calibrated data. You'll have these very large sort of exposures that will come down as raw images. You will have access to these. These will be delivered to the archive. We'll do a basic, what we call ramps to slopes. So you'll end up doing bias subtraction, dark subtraction, etc. And then you'll fit a line to that slope. So however many groups you have. If you only have one group, there's no line fitting. you just get your ADU per second. And you'll have access to those calibrated ramps in the archive as well, if that's where you want to start your analysis. Those data will then flow down to higher level processes that will do things like flat filling. It will also give you your wavelength solution. This phase right here will also make rectified spectra. And then finally, those data products, which are still fundamentally three-dimensional, so it'll still be a 2D image, and then as a function of time, will flow into our own private playland for transits called CalTSO3. And this whole system is built in Python and meant to be modular, and you will have access to the pipeline after the fact if you want to reprocess your data. In CalTSO3, there will be spectral extraction, and you will be delivered extracted spectra. You will also be delivered white light curves. So you'll have this quick look data product that will help you to understand what all the systematics are. And I've put some of the stuff that's going to be delivered to the master archive. There's also a lot of work going on right now to make the master archive a little bit more friendly for exoplanet observations. So, stay tuned. Soon you may have an interface that allows you to look at your quick look white light curve so you understand, is that a transit or eclipse observation or a phase curve? And collect all of a single planet's data in one place. All right, so here is the timeline. And this is the part where I hope you all understand that it's coming a lot more quickly than you may think. So there's a guaranteed time observers call for proposal release that's going to happen in January 2017. And then the GTO, the guaranteed time observers proposals, are going to be due in 2017. You should note that the GEO cycle 1 observation release, yes. The GEO cycle 1 call for proposals will be in November 2017. All right? So that's when you have to start actually working on your proposals. It's coming soon. And your cycle 1 deadline will be in February 2018. Okay? There'll be a TAC that will decide which observations are going to cycle 1, and then that will happen before launch and then commissioning. And then cycle 1 will begin in April of 2019. I want to highlight something called the Early Release Science Program, which is actually a bucket of director's discretionary time that has been earmarked to have programs that will enable observers to test out all the various different modes to figure out how to operate them most efficiently. And that should enable you to rapidly make progress on your own observations or consider proposals for cycle 2. There will be no proprietary period on these observations. So they'll be taken in the first 6 months of operation, and they'll be available to everyone. So then you can go process whatever transit observations we have for NearSpec or NearSc, et cetera. I'll note that there's a group that wrote a paper that had sort of what we thought was the optimal strategy for transits in terms of early release science. And so I encourage you, if you haven't read this document, to go look at it. The basic theme here is to find a target that is in the continuous viewing zone so that we can use that single target to exercise all the modes to have a consistent look at the way the various modes operate at all the wavelengths. And these targets that we identified in this proposal will actually be observed with HST in the near future. They were selected in cycle 24. All right. So there's lots of other resources out there. The Bikeman et al. Paper in 2014 came out of a very nice workshop that occurred here. It has really, I use it actually, really great information understanding JWST operations for JWST operations for transiting exoplanets. So I encourage you to go here first. This is a good first place to stop. We have a new revamped website at Space Telescope for the at Space Telescope Science Institute for the Webb Space Telescope. Has a lot of neat new science planning stuff here, so I encourage you to go there as well. There was a workshop that was held in November of last year, which is where this ERS paper actually spawned from, and all of the talks were webcasted and recorded, and all of the slides from the speakers are available at this link. So you can go through at your leisure and look at the mix. It was really a mixture of science talks and also trying to understand the operations of JWST for transiting exoplanets. Okay. There will be another Transiting Exoplanet Science with Webb workshop that will occur in the summer of 2017, so stay tuned. All right. So I just want to finally highlight the sort of key questions that we're going to address with JWST very quickly. And just remember that JWST is really going to revolutionize exoplanet science. We're going to answer long-standing questions about planet formation and evolution. Yeah, I think most of you have seen this plot before. We're going to add a whole heck of a lot more points to this line or non-line. We're going to get some of the first looks at rocky planet atmospheres beyond our solar system. So here are those observations of 1132 with 10 nearest transits and 10 Miri eclipses. Perhaps my favorite is we're going to be able to probe climates of distant worlds. I'm looking forward to phase curve observations to understand really what these climates are like beyond our solar system. And of course, it's going to help us, get one step further along the path to answering the question, are we alone in the universe? So I'll take questions. So exoplanet science has always been a collaborative place. I am a planetary scientist by training. I am not an astronomer, quote unquote. So certainly in the era of JWST, there's going to have to be a lot of more interactions between different communities, the observers, planetary scientists, Earth scientists, understanding climate in the temperature regimes that are relevant here. But a lot of that will happen naturally and evolve in that way. And I think there are a lot of efforts out in the community right now to push those interactions. The Nexus initiative is one of those that's really starting to bring in lots of different communities to attack this problem for exoplanets.
Nikole, in Pandya, you showed that there's a planetary spectrum that was then noised up, noised model. Is that something that's being generated for us by Pandya? So it's a great transfer model, or are we allowed to present our own?
You can put your own planet. Oh, sorry. The question was in Pandexo, do they give you the planetary spectrum, or can you input it? Is that basically the question? Yeah. You can input your own. When we release Pandexo, it will come with a basic set of generic planetary spectrum if you want to just ballpark it. In the same way that the NearSpec tool uses a generic hot Jupiter and scales it. But that really allows a lot of flexibility because people have their own atmospheric models and they may not want to be stuck with the ones that we provide them.
It looked like the early release proposal timeline overlapped with the guaranteed time.
Yes. Yes. So that's right. There's been the question was someone noticed that the early release program has a significant amount of overlap with the GTO call for proposals and deadlines. There's about I guess 1 or 2 months in between when the targets for the GTOs are nailed down and when the proposals for the early release science are due. That requires that there be a lot of communication between the community and the GTO stakeholders, because if the GTO stakeholders choose a given target, they get priority. And that conversation has already started for transiting exoplanets. And at this point, the targets that have been identified, at least in the Stevenson et al. Paper, as sort of the top 4 targets, are not currently part of any of the GTO observing plans.